Good afternoon, Dr. Rajan.
Sir, good afternoon, sir. Dr. Shaktivelan, sir. I'm Shobna, sir.
Yeah.
Sir, people are joining, sir. Can you wait for 5 minutes, sir?
Yeah.
Is it fine? Right.
No, it doesn't matter.
Yeah, sir. Fine, sir. Thank you, sir.
Shobana? Shobana?
Sir, yes, sir. I'm here, sir. Good afternoon, sir.
Good afternoon. Good afternoon. Sir has joined, huh?
Yes, sir. Sir has joined. Now only spoke to Dr. Shaktivelan, sir. I asked for 5 to 10 minutes, so people
Yeah,
are
we
joining,
wait.
sir.
During
Yes,
lunch always takes some time.
yes, sir.
Shaktivelan, sir,
Okay. Yeah.
don't mind. Some 5 minutes will wait, sir. Huh?
Okay, no issues.
Thank you. Had a lunch, sir?
Not yet. I will take after the session.
Okay, sir. Shall we start? Sir? The time is running out. Let people join, believe. I will start. Sir, please, you can start your presentation.
Okay, shall I start now?
Yeah, sir. Fine, sir. You can
Okay.
start, sir.
Yes. Okay, is my PPT visible?
Yeah, sir. It's perfectly visible, sir.
Okay, the present topic is on multi-criteria approach for maintenance management of highway networks. Do not worry about the lengthy heading. Okay, so what I would like to say is simply I would like to talk about pavement maintenance and a scientific approach. That's all. As you know pretty well, managing a 59-kilometer of road network over the entire Indian peninsula is a challenge for highway engineers. You know pretty well the pavement deterioration due to various factors is there: traffic, climate, environmental factor, and so on. So all these are inevitable. Is it not so? Delaying a maintenance treatment implementation results in high direct and indirect cost. So therefore, if you repair, it is 6 times after 3 years of neglecting a maintenance.
Sir,
Yeah.
Shaktivelan, sir. Once again, sir. Sorry for interruption. Sir, your face is not fully visible, and sir, you can just move your camera a little bit up, sir, so that your face is clearly visible.
Oh, my face. Is it okay?
Yeah, sir. Fine, sir. Perfect, sir. Thank you, sir.
Right. Am I audible? Is PPT is fine?
Yeah, sir. Fine, sir. Your voice is
Okay.
clearly audible, sir.
Okay. That is more important than my face.
Yeah, sir.
Right. Fine. Repair cost. Repair, as we are talking about, repair cost is 6 times after 3 years if you neglect the maintenance. Right? Is 6 times. Whereas it will be 18 times when you neglect after 5 years. Choice of appropriate maintenance treatment and its timing are very much important. They are very much key for an effective maintenance system. As you know, the pavement deterioration, it deteriorates into various factors like traffic, environmental factors, as I was telling you in my previous sessions, like ingress of water, oxidation, loss of volatiles, and inadequate in the initial structural design, poor construction practice, and there is a lack of inadequate support at the lower pavement layers. Therefore, lower pavement layers also very much important. Inadequacy in the surface and subsurface drainage, lack of good quality control. Your maintenance planning, as far as the planning is concerned, it is a major categories. It is as 3 types. One is a ranking. So you have to rank the each projects in any of the set criteria, and you rank it according to that. Then finally, you select this for maintenance plan. And another one is a prioritization. So you have to now consider some benefits of the maintenance, and you prioritize. And the projects are sorted for each and every year. And there is a chance for backlog of due to prioritization. And the third one is called as optimization. In optimization, you consider all things over for multiple years. Over the planning horizon, you will take everything into consider, and you will optimize. So this is the most effective method of maintenance planning when compared to all these 3. So here I would like to say that this is the performance curve. So this is the performance curve. The condition initially will be excellent, and it after that it falls down, and finally to the failing it. But you can see that initially the slope of the curve is very slant, not a steep one, and later after a particular time the slope is steep. What does it mean? Therefore, the failure rate is more here. In other words, the deterioration rate is higher, whereas here it is very less. Therefore, when you maintain certain things, it will be a unit cost. But after sometimes when you maintain it, it will be 5 to 10 times of this cost here. Therefore, earlier the maintenance would be better. That is the general case. So how maintenance are done usually? So this is the different phase of the life. This is the time and this is your performance level. But initially, it is the slope is very meager and later it falls down and finally it ends to the what you call inserviceable state over a period of time. This is a period of time. Therefore, what happens? Usually, the preventive maintenance will be done at the initial phase. So where the slope is normal, where the slope is, in other words, where the slope is meager. But in the intermediate stage, you will have a minor and major rehabilitation. Minor and major rehabilitation. So in the latter phase, you will provide a reconstruction. Okay, this is a reconstruction. Therefore, this is the phenomenon. So a preventive maintenance is provided in a structure or in any system, right, where it's a structure, it is structurally good, but functionally it may not be good. Therefore, in such cases, you can provide a preventive maintenance. Therefore, when you want to make your system to regain its original strength, structurally as well as functionally, you can go in for any rehabilitation or reconstructive measures. So our scope of investigation is, so we will be finding out what are the different distress criteria and how it can be investigated and you can be considered into the optimization process. The second one is we have to take into consideration both functional as well as structural, which have not been considered earlier in the optimization. Then we should also consider about multi-objective optimization. Usually a single objective optimizations have been considered over the period of time. So we can consider multi-objective optimization. And in multi-objective optimization, one of the best method is epsilon constraint algorithm, and this will provide effective in generating a non-dominated solutions. Okay, but it has hardly been used in the payment maintenance optimization because for two reasons. Number one, multi-objective optimization itself have not been considered. Even when in the multi-objective optimization, they have considered in a different ways to ease out the process. Identification of the posterior maintenance scheduling strategies from Pareto frontier. Okay, once you get the Pareto frontier, so maybe I may use a little jargons, but you will come to know it will be, it's not that much jargon as you think about it. These are nothing but non-dominated solutions by some distance metrics. Okay, you can identify the scheduling strategies, and other optimization process can also be thought of. Other optimization approaches can be thought and can be used suitably for the different scenarios. The present study's objective is to find out the structural and functional distress criteria to be incorporated. Next, we have to find about the timing for the preventive maintenance intervention. Third one is to formulate multi-objective optimization model. Third one, you have to think about other alternative strategies. And you have to finally, you have to provide a framework and to decide the suitability of the alternate optimization techniques for the maintenance management of the highway networks. So as far as the scope is considered, we will be using the structural condition of the payment by considering the rebound deflection, using a bending membrane beam test. Functional condition from the roughness that can be obtained from 50-wheel bump integrator. And we should be having the pattern of the distress progression. Okay, how the distress gets progressed over the period of time. And at the same time, you have to find out how it is, how a particular treatment is responded by the payment. Both the things have been taken from the literature. Okay, and of course, this will be validated later. Discrete time period is taken as 1 year. For every year, we will be taking the response of the payment, and the treatment also will be done at the beginning of the year. That is what we have been considering. Okay, that in other words, I can tell that we will see that let the deterioration goes first from the beginning to the end. Then at the beginning of the year, what we'll do, you will make on some treatment. Then again, deterioration will go. So that is the order we have taken. Then mathematical formulation is done by integer linear programming. Okay, integer linear programming is nothing but it's a technique in which integers are also involved. Not only, see, we will not get an optimized result as 32.78, okay, or 42.65. It is an optimal, but instead that it is whether 38 or 41, like that, a full number is considered here. Why integer linear programming? Because we are considering the treatment choices as an integer. Therefore, we will not, for example, treatment choice 1, treatment choice 2, treatment choice 3 is there. We cannot say 2.3 as a treatment choice, because that is not possible, but it is easily possible in optimization. But therefore, we are using something called as integer linear programming. And the other things like transition probability matrices and differential algorithms have also been used. Data source. Okay, as I was telling that the progression pattern, progression model have been taken from literature, Reddy and Birraghavan 96, and similarly roughness from Murali Krishna and Birraghavan 2011. And similarly, we get the effectiveness, the response of the payment for deflection for various treatments from Lister 1972 and roughness Irfan et al. 2009. Of course, all these models have been field validated from roads of the Kadalur Division Highways Department. And of course, there are some models which is not matching it. For that, two methods have been found out. We have taken the roads which matches with the model, number one. Number two, we have changed the regression coefficients in the model. These are the two things we have made. The field data, so the road networks corresponds to these 7 roads here, and performance data have been taken from fifth wheel bump integrator and Bengal BEM, as I was telling you. Historical and maintenance data from roughness progression, deflection progression, treatment effectiveness, all from taken from the models and have been validated. So this is the methodology. Okay, so for that, what we have to do is first you have to identify what are the distresses. You have to identify what are the distresses and how these distresses gets progressed over the period of time. So every year how it gets progressed, because we know pretty well every distress will start at a particular value, and every day, every year it will get increased only. Okay, then and we have to model. We have this model, and we have to get this model validated from the field data. Similarly, we have identification of the treatment choices. We will have to identify what are the treatment choices that have to be made to these payments or roads, and these treatment choices, how these treatment choices affect the payment, how performance gain is given, what is the advantage of doing this treatment, by doing this treatment, how this distress gets relieved. That we have to have this model, and this model should also get validated from the field. So for that, we have to select the particular sample network, and we have to find out what are the historic data from the network for both the distresses as well as the treatment effectiveness, because these distress and treatment effectiveness data will be used for model validation from this model as well as from the treatment choices. Okay, once this is over, we have a validated distress model and validated treatment model, and we will be finding out for different treatment. We will have a cost treatment matrix for different roads and different treatment choices. We will have a matrix of cost. What is the each cost for different treatments, and we'll have a user inputs. What is the present condition of the payment? What is the present condition of the payment? And it is a user input, and based on the present condition, only the distress gets progressed over a period of time, and the treatment will be given at an appropriate time, depending upon the optimization process. So this is the methodology continued, and we have the optimization here. This optimization process can be done in any of the methods, any of the approaches. Number one is your mathematical modeling. Mathematical modeling is purely an analytical model you should have, and this model may be a linear programming or non-linear programming or dynamic programming or mixed integer linear programming or integer linear programming, whatever the way you call that. You will have a different types of programming there, and the models have to be made. And moreover, this have to be done for not only for a single objective, we have to make it for a multi-objective optimization. Therefore, each mathematical modeling have to make it for a single objective as well as for a multi-objective scenario. Therefore, in case of multi-objective scenario, what we are doing is an epsilon constraint algorithm. In the epsilon constraint algorithm, it will produce a different set of non-dominated solutions or Pareto solutions. These Pareto solutions will be the minimum most solution that one objective can be will be the maximum one. When you want to increase that objective performance, there will be a loss in the other objectives performance. Therefore, that is the way. Well, it is we will get in what you call extreme edges of the mathematical modeling optimization for the multi-objective scenario, and this can be done with a meta-heuristic concepts. Okay, there are meta-heuristics available. What is meta-heuristic means? In a mathematical modeling, there is a difficulty in doing the mathematical modeling for a larger networks because of the computational effort. Because for a larger network, the computational effort will be large, even for a 10 rows. Even for 10 rows and 10-year planning, it will take more than 2 weeks for running the program. Therefore, we have to model in a different scenario where we will lose little optimality, but we will definitely end up with some good solutions. And of course, that good solutions will be a preferred solution by the institution. The next one is called as TPM approach. TPM is this is nothing but so we can do it by both the mathematical modeling as well as the differential evaluation algorithm. Both are a deterministic approach. But whenever you find out it is not possible to have a differential for a deterministic approach, when you want to add the variability into the as a component, or you want to make more uncertainties to be considered into the process of optimization, you can go for a Markov chain or a Markov process. Okay, so we have produced the transition probability matrices based on the Markov chain, and that is used in this optimization process. The final one is a simulation. This is usually simulation can be done, but system dynamics is a separate type of simulation wherein a dynamic component can also be considered in the simulation, and the various process can be taken into it. So, and moreover, there are different softwares available for the system dynamics which can consider optimization too. But at present, there is no good software which considers a multi-object optimization or optimization with the particular mathematical modeling or any other specific modeling. They use only something called as evolution algorithm. Okay, based on evolution algorithm only, they have those optimization process. Okay, fine. So in a mathematical modeling, what we do is we will consider the time, we set time to 0, and RB is nothing but we have two different, as I was telling you, we have two distress criteria considered. One is a roughness and another one is deflection. As you know, roughness is how the pavement is seen. So it may be a rough or a smooth one. A smooth or rough pavement is considered as a good, and rough over the period of time the smoothness gets worn out and we get a rough pavement. Therefore, roughness, a lower level roughness and a higher level roughness. Lower level roughness is a good one, higher level roughness is towards the failure. Similarly, deflection. Deflection is nothing but how it deflects for a particular load. For example, what we consider is a Winkelmann deflection. To be more simple way, see if the pavement is good, it will have a lower deflection. If the pavement is bad, it will have a higher deflection. Therefore, lower deflection means you have a good pavement. So, for example, but what happens now over a period of time, even roughness as well as deflection also increases, because it means this checks that it is functionally and also structurally deteriorating. So, roughness indicates the functional criteria and deflection indicates the structural criteria. Okay, well, that's what I put as two criteria here. And over the period of time, see, roughness and deflection increases as a function of R0, D0, means initial deflection and initial roughness and under time. Similarly, deflections. Okay, this is what you find out at the end of the year, at the end of every year. Then you find out this every year deflection, you find out set as beginning deflection and that is before treatment, deflection before treatment, roughness before treatment. And you apply some treatment, you will get deflection after treatment and deflection roughness after treatment. Okay, then you go to recycle it for a next year. So for every year you recycle the same process and you interact with the optimizer. Okay, some solver you interact with that, then you will result with what is the distress level over the period of time, what is the total maintenance cost, how the scheduling is done. That is whether what is the treatment done for each year. That is what I mean as scheduling. Okay, so what you have to give in your optimization solver, you should provide what is your threshold distress. So that is you should fix that your roughness should not increase a particular level, and you can provide what is the treatment cost. Okay, what is the treatment cost for different treatment choices here? Okay, so based on these treatment choices, this cost will be taken care, and you will find out the total maintenance cost. So when your constraint is to limiting the distress or budget, this can be done in either way. You can either limit the distress level and find what is the cost. You can limit the budget, you can find the what is the distance level. In both cases, it is possible. So this is the basics of your mathematical model. Accordingly, as I was telling you, first you have to find out what is the model validations, and for detailed models you have roughness progression and deflection progression. Treatment effectiveness, you have both roughness effectiveness as well as the treatment effectiveness, and these are the 5 treatment choices I have been considering for this process, optimization process. One is do nothing with a routine maintenance. Another one is a thin overlay. Thin overlay means yes, there's some hot mix asphalt you have of 30 mm or 40 mm thickness, very thin overlay. Thick overlay of 75 mm thickness, some mix maybe added into your binder course. Then rehabilitation, this is also possible. So in rehabilitation I consider as 150 mm thickness HMU. And the final one is you redo the work, reconstruct. Okay, that is the 4 choices I have made for this. So how this optimization select each one, we'll see. First, before that, what we have done is before making a full model, initially we have made the model to work it for a preventive maintenance. Okay, the preventive maintenance is applied for a structurally good payment to enhance the structural life of the, to enhance the service life of the payment. It means it will enhance only the functional capacity. Okay, so for example, if the structural payment, if the deflection level is very low, lesser than 0.3 like that, so but your roughness increases to 2000 to 3000 or 3200. In such cases, you can go for a preventive maintenance. Okay, so for this preventive maintenance, when you have to make it first intervention and its frequency have not been quantified. Similarly, the functional distress only considered. Because for the same reasons, functional distress is sufficient because structural distress is not required, because structural, you assume that structurally good payment. Okay, so then you have to use a binary integers in your NLP. Okay, because the Excel solver we have only NLP, because it is a non-linear programming here. You use only binary integers for this, and using Excel solver we have been using this. Okay, so for the objective is maximizing the benefit area. Maximizing its benefit area is, I will tell you what is the benefit area. Okay, so we can find the extended and improved service life, time to rehabilitate the treatment intervention, and number of maintenance intervention. Okay, these can be the results we can find out. So this is how it goes. For example, these blue dotted lines, blue lines says that you do anything, you don't do anything without any preventive maintenance. Okay, there is the progression of roughness will be like this. It will progress like this. After 5200 also it will progress, but I make 5200 as a terminal level, because after 5200 millimeter per kilometer of roughness, it is found that it is unserviceable. Okay, not safe to service. Therefore, I take that as a safe life and considered for the optimization process. So when I make an optimization process, but it will do an intervention like this. For example, at the end of 5th year, there is an intervention. Therefore, post intervention progression is like this. Okay, after intervention, it will progress like this. Okay, and it will reach the 5200 level. So now you find out the area between this, the do nothing curve and preventive maintenance curve. Okay, that is an area. This area is called as benefit area. Therefore, when a benefit area is more, it means your maintenance strategy is very good. When a benefit area is very less, the maintenance strategy will be very less. For example, see, for example, if it goes like that, it falls like here itself. So it means benefit area will be very less. And you can find out what is the extension of life. See, originally it fails here, now it fails here after treatment. Therefore, you get an extended life of 5 years or 4 years, like that. So therefore, if it is less, the benefit area will be less. Okay, that is what I would like to say. So now we will compare two types of payments. One payment is traffic level is low, 2900 CVPD, and another one is 3500 CVPD, and we have R naught and D naught, that is initial roughness and initial deflection level is 2.2 meter per kilometer and D naught is 0.45 millimeter. Similarly, here is same, both are identical, and you find out only what is the change, only the traffic level. See how payment life changes here. See, life extension is 4 years, and the first intervention is 5th year, and the benefit area is so 9454 millimeter per kilometer. Whereas here, what happens? Life extension is 3 years, first intervention is 3rd year, benefit area is 9114. Okay, therefore it shows that when comparing these two, the traffic level influences the what do you call it? The intervention time. Okay, when the traffic level is more, the payment strategy is different, but both are optimal only. Okay, both are optimal only. Because of the traffic level, the life extension reduced to 1 year. I mean, reduced by 1 year, and benefit area is also reduced. Second case we'll see. So there is an identical traffic level. There is an identical traffic level, but initial payment condition is different. So initially is 2 and 0.25. This is 2.2 and 0.45. Therefore, this is an extremely good payment. And when it is compared to this, it is not that much good. Okay, we can say as a excellent payment and a good payment. We can say like that. Okay, so in such cases, what happens? You see here the life extension, the area you can see larger area, here a sharper area. So life extension is 6 years. First intervention is also 6 years. Benefit area is 13490. Whereas in this case, you can find out life extension is only 3 years. First intervention also 3rd year, and benefit area is also less. Therefore, what we can let's say is initial payment condition matters. Okay, initial payment condition matters. So if the initial payment condition is very good, it means if it is structurally adequate payment, the maintenance is it has a longer life for maintenance, and maintenance benefit area is also more. Okay, that is what I would like to say. Therefore, you have to make the payment good at the initial itself. So how this can be used? Okay, this can be used. The preventive maintenance is sensitive to traffic level as well as to the initial condition of the payment. That's what we have seen. Both are, it is sensitive, but it is more sensitive to initial condition of the payments. Okay, initial condition, it is more sensitive to the initial condition of the payment. Similar approaches can be made for different slurry seal or mixed seal surfacing or micro surfacing or fog seal. Okay, these are the different preventive maintenance strategies, and you can apply for these things for our road conditions. You can find out what is the benefit area for each one for your road. Okay, and you can find out which one is suitable for you. Okay, which one is very much suitable for you, which one gives you a higher benefit area, which requires a longer intervention time. Therefore, that way you can use this model to choose your preventive maintenance strategies. Therefore, this works out, and hence a full mathematical model can be implemented. That is what we have identified from this. How a full optimization model will be? So I was telling you that generally we can consider as one is a deterministic approach, another one is a probabilistic approach. In a deterministic approach itself, we have two types of models, two types of scheduling models. The first one is called as budget bound model. Budget bound model means your budget is as a constraint. You have a budget constraint. You have to minimize your distress levels according to that. Okay, so that is what usually the government will give. The government will give. It will provide a budget, and you have to make the system according to that. You have to maintain the system according to that. So therefore, you will be in such cases with the given budget, you will try to minimize the average network distress level, or you will minimize the maximum network distress level, both. So you will have maximum network that you will minimize. Okay, both are possible. Similarly, another one is called as necessary fund model. So in that case, as limiting, you will be limiting the network distress level, considering the considering the cost. So what you will do, you will minimize the cost. In such case, you will minimize the cost, but you will limit the network distress levels. Therefore, usually in a private consortium or private working style, they will, what you will do, they will try to minimize the cost. Okay, they will try to minimize the cost because they have the constraint to have a particular distress level to be kept. Okay, they should not increase the distress level beyond a particular level. Therefore, in such cases, what you do, these things will be kept as the constraint. Therefore, your distress levels will be kept as the constraint. That may be your average network distress level or a maximum network distress level. You will both, or same, or anyone you will keep as a constraint. And there is another one is called as invoking a trigger level. Okay, in either of the cases, next to one is called as invoking trigger levels. This is nothing but a particular level of trigger is a particular level of distress is reached. Okay, particular treatment will be invoked. Okay, for example, if the roughness level increases more than 2,800 and deflection level more than 3 mm or more than 0.4 mm, then you can go for a preventive maintenance. Like that, something one can make. Okay, that is called as a trigger level invoking, and you can optimize also. You can invoke the trigger levels at the same time you can optimize also. That is also possible. So this is an implementation of the road network. So we have considered about some roads with varying traffic levels. See 2850, 850, 570, 285 like that. We'll have a MSA, different traffic loading, 100 to 10 MSA. Length of roads also varying, 8 to 16. Number of lanes 2. Age, the age is 1, and you have a initial deflection levels like this. Okay, and this is the unit cost of the treatment. You have a different unit cost of the treatments. We have 5 options, and for road 1 to road 4, you have a different cost in millions per kilometer. So in a mathematical modeling, see, either you can have a single objective or multi-objective. As the problem is more, will have a large number of solutions, we cannot do manually, number one, or with the available free softwares. It is not possible in both. So you have to use the software called as Cplex. Okay, IBM is providing that software. Therefore, that Cplex software you use, it can accommodate more number of variables. So accordingly, you can use that. Even with the Cplex software, so I have used about 1 lakh variables here. And see here in a multi-objective scenario. So what you do is, for each objective you will plot. So this is objective number 1. This is objective number 2. For example, you can say as deflection here, roughness here. Okay. What happens? You will do. You want to minimize the deflection and you want to minimize the roughness. Both are means your curve will be like this. This will be your curve. F minimum and F2 minimum, F this minimum. For example, there is some other scenario. Okay. For example, benefit and benefit here, and you have a distress here. But in such cases, what you will do, you will maximize the benefit. Okay, you will try to maximize the benefit and minimize the distress. So in such cases, the plot will be like this. Okay, the other combinations are, if you want to maximize both, so this will be like this. And if you want to maximize the x-axis and you want to minimize the y-axis, this will be your frontier pattern. Okay, therefore I have made a single diagram to identify how the pattern for a different scenario is concerned. So in a multi-objectives, you have F1, F2, F3, like that. You have different objectives. You want to minimize these, and what you will do, you will keep one thing as objective, and other things you will given as a epsilon constraints. and you will do repeatedly on this, and you find out these different values here. So first we'll find out a necessary fund model. Necessary fund models, as I was telling you, our aim is to minimize the maintenance cost, and your constraints will be network roughness will be lesser than the you will be fixing on limiting roughness, so it should be lesser than that. That is your constraint. Network deflection you should keep as a limiting deflection. Okay, you can put as average network left or maximum network like that. Okay, accordingly you will find out like this. See, minimize. Okay, minimize the cost subjected to the total cost. See, over the period of 1 to t and 1 to n, this is a cost of tn. Means for t is over the period of time for over different roads payments 1 to n. We have different payments for we have 4 payments means 1 to 4. We have 5-year planning period means 1 to 5 like that. This is what this shows like that. Similarly, this is the constraint. You will find out what is the total constraint here. You will find what is here. At every year, you are finding the beginning roughness, end roughness for every year for every roads divided by 2. This is nothing but average for the over the period of time over all roads. Okay, over all roads. This is the total average value, and that is lesser than your threshold average value. And likewise, the threshold or a limiting deflection value. You will be doing like this. Okay, this is the way that I have pointed out how the model will be. And similarly, you have a different variant. And another one is I put as maximum network, maximum network roughness. What you do is you find the what is the maximum roughness network for each year. You find out what is the maximum level, and that should be lesser than. For example, 1 year it will be 2000, another year 2800, third year 2600, fourth year 3400, fifth year 2000, like that. If that is the case, what is the maximum there? 3200. That 3200 should be lesser than your threshold value. That is what it means. But here you will find out all these values and divided by average. That is the model here. Therefore, this is more a stringent constraint than this. This is a more stringent constraint than this. So third one is trigger models. Trigger model is nothing but what is required is you should find out what is the typical trigger values, or this is the policy of the organization or policy of the department. See, for example, a typical trigger values I show here. See, up to 0.5 and 2.8 roughness, 0.5 of deflection, no need for treatment. Only first do nothing is sufficient. And treatment 2 is initiated after 3.2 and up to 0.5. Therefore, after that, between 0.75, even for 2 deflection, if the deflection exceeds 0.75, initiate third thick overlay. And the fourth one is initiated at 1.5 at even the minimum roughness. So like that it is. And you have to rehabilitate when it reaches 2.5 and 4. So like that. So there are some white spaces there. Mostly that will not come. That is what such cases does not arise. Okay. So for example, 1.7 for 2 that may not arise like that. Okay. So accordingly, what happens? You have to find out what is the total cost, and delta T NIA is nothing but that how it is selected, and that is for a T means time, N means N, I means row and column of this, A is a treatment choice. So accordingly we will select, and what we'll do is in this matrix, what we'll do, we will provide higher cost like CIJN. We'll provide a higher cost for treatments higher than what you require. For example, 1111 is there. For all other treatments between this and this, right? You provide a higher cost so that will not be considered in the optimization process, because you are making a minimization process. You provide a higher value. You voluntarily provide a higher value there, but when you consider the optimization, it will see the higher value and it will not consider, and it will consider only up to this, and higher treatments will not be considered. Therefore, when it changes this path, therefore other treatments will have a higher value, and only this treatment will be selected. That way we make the optimization process to change. So here it is a technique we make the optimization to change according to the way you think. Okay. Here in the previous case, right, you make the optimization process, okay, on the way you want. Okay, and you cannot do you cannot change its path. Okay, you should make it along with that, and you try to get the advantage of that. But here you can change the path itself. That is what this model gives. So on implementations, we have a the annual cost, like the year 1 to year 4. Okay, in variant 1 and variant 2, both gives 464.8 millions, and the threshold deflection is 0.6 to 3. So these are the treatment strategies we have. You can see that only 3 and 3 here. Okay, and there is no other treatment here. Okay, for other things, do nothing. Only for road 3, 3rd year, and road 2, 4th year. You give only 75 mm thick HMA, and no other treatment is required. That is what say. If you do like that, the threshold deflection of 0.6 and threshold roughness of 3 meter per mm is not exceeded, and the minimum cost required is 464.8. This is what. Similarly, necessary invoking triggers also we have merged with a different trigger values. I have plotted here. And what is the main application for the necessary fund model? Sir, in a necessary fund model, so one of the best application is to find how the effect of deferred maintenance. Deferred maintenance is how whenever you change the maintenance, when you want to maintain a particular time, you have to maintain that time. If you delay it, so what will happen? That is what, right? That is what I made. For example, we have considered 2 types of payments. One is a structurally inadequate payment, and another one is structurally adequate payment. In both the cases, we made a necessary fund model, and we have made the optimization process. See how it goes like here. See, we will find out both average deflection and maximum deflection. See, this is the optimized level. This is 0 is the optimized level. Therefore, if you delay by 1 year, what happens? Your maximum deflection increases, and the average deflection also increases. Delay by 2 years, it is further increases. Delay by 3 years, it is further increases. 4th year also, it increases. Therefore, every year it increases. Therefore, do not delay more than the optimized level. Okay, but it is to be noted that, and it is very much surprising that even a preponing also make the same effect. Okay, therefore you can see a increased effect or preponing time. Therefore, even if you prepone by 5 years, it is not good. Even if you prepone by 4 years, it is not good. Therefore, what you do is, okay, do it in the optimized time. That is what is required. Therefore, doing a payment maintenance in an optimized time, even before or later, is not good. Therefore, an earlier intervention or a delayed intervention, both is not good for the payment. That's what it says for a structurally inadequate payment. Okay, we'll see what happens to the structurally adequate payment. See what happens. These curves get flattened. What does it mean? It means that the effect of intervention, okay, by delaying 1 or 2 years, is not matter that much. Okay, therefore you can see there is a very little change only here in both the cases. Okay, therefore for a structurally adequate payment, okay, there is a window time available. You can say there is a window time available. You can go here and there. You can delay for 3 years front and back. Okay, you get the advantage of the window period, provided that the payment is structurally adequate. Okay, structurally adequate. Therefore, structurally adequate payment, structurally initial payment condition is good. For example, 0.25 and R0 is 2. Initial payment condition is very good. Okay, for such cases, okay, the maintenance, there is a maintenance intervention. Okay, maintenance intervention. So I can say that you can say buying a vehicle. Okay, get a good vehicle. Okay, the maintenance will be more. And get a bad vehicle, you can see how maintenance is there. Okay, for example, for a second-hand vehicle, initial structural condition is bad only, na? So you can take the second-hand vehicle and treat that the first year is as an initial structural condition. So it is bad. Therefore, if you don't do maintain properly, the deterioration will be more. For a new bike, you can see it goes like that. Okay, this is the way I would like to say. In a budget bound model, the second one is the budget bound model. What I would like to say, the budget bound model is the model in which budget is kept as a constraint. That means, the Indian scenario, pretty well. Or budget is always fixed, so we have to make it here and there, do something, finish it within your budget level. That is what everyone like. So and we have to make the model to that extent. We have to satisfy that condition also. So that is the case here. So we have a two budget model, and so considering number one, average roughness. You are minimizing your average roughness. You are minimizing your average deflection. That is, both are your objectives. You have two objectives here, but it is a bi-objective problem. You have minimizing or minimizing the, what is the budget condition? This is your concern. So over the period of time horizon over 1 to n, that is number of roads. For all roads over all years, find the treatment cost and sum up it, and that should be lesser than your full budget. This is your overall budget scenario for that. So this can be done as another variant as minimize the maximum roughness, you can minimize the maximum deflection. Both are possible. Okay, this is two objective and it is constrained for the budget. Okay, and there is one more further variance is also possible. What is the further variance? You can provide a uniform annual budget. Okay, so what you do is, I am going to provide an annual budget instead of a total budget for total years. Instead of B for totally 5 years, I want to give for each year, I am going to give a budget. So that is also possible. In such cases, this double sigma will not be there. Instead, you will have a single sigma 1 to n for each year budget year, for all budget varying from 2 to t. First year is left free. That is what I did put. First year is only you are allowing your payment to deteriorate. That's all. From second year only your budget comes. Therefore 2 to t. That's what I put. Okay. Similarly, if it may be annual budget, a uniform annual budget. That is, B of t may be uniform. Maybe, for example, 100 crores every year budget. That is a uniform budget. So, for example, there will be a variable annual budget. That is also possible. For example, this year 80 crores. Next year 100 crores. Another year 120 crores. Next year 200 crores. Like that, you can make it for 5 years. That can also be possible. Okay. For every year you give prior itself, a priori, known a priori, and you can design, you can optimize for total 5 years. Okay, but every year budget is given to you. That is also possible. So in such cases, you have to go for something called as epsilon constraint algorithm. Okay, this itself is a separate topic, and we will discuss it when time comes. Okay, meanwhile, you just go through your any literature and find out how the epsilon constraint algorithm is, and it will provide what is the average network deflection and average network roughness in a different levels. Okay, for example, your budget is 450 millions. Okay, for millions. Therefore, what you do is, within that budget, I found out a minimum most roughness and minimum most deflection. 2.035, 0.397, and 2.05, 0.377. Another scenario 2.1, 0.355, and the fourth scenario 2.13, 0.351. You have 4 different scenarios. Okay, you can see that it comes like that. Okay, so because it is both minimum, okay, it will be like this, and you have to find out which one is the best. But it is fantastic to know that all 4 will be the best one, because when multi-objective scenario, all thing will be best. Okay, all you want both, na? So you want both to minimize both this and that. Okay, yeah, in such cases, all things will be good only. But there is something called as preferred solution. Okay, being a user or being a owner, okay, you can prefer, because being an analyst, what we'll do, we will give the scenarios. I am giving you scenarios. See, this is the budget. You have given budget as 450. I am giving you 4 solutions. Or 4 solutions are good. You can select any good solution. I am giving you a choice. You can select any good solution. Being a user or being a owner, you can select one of the best solution. Okay, one of the best solution among the best. All these are best, and you can choose any. So how to get a best solution among these best. Okay, so that is used called as knee point concept. Okay, knee point concept. So we have different Pareto solutions. So solution 1, 2, 3, 4. I have got 4 solutions here. 1, 2, 3, 4. And accordingly, the scheduling is like this. Road 1 for up to 4 years like this. These are the schedules. Okay, and these are your treatment choices. 1 means do nothing. 2 is interfacing. 3 means HMA, 75 HMA. Only these things are there. Treat all 4 solutions are good. You can choose any. But the best solution, again you'll see these are the cost for each one. Okay, now you'll see that is called as knee point concept. We have 1, 2, 3, 4 solutions. Okay, what you do is put in a horizontal axis, put in horizontal. Therefore, this is your reference point. Okay, this reference point is called as ideal point. This is an ideal solution. Okay, this is an ideal solution, and you put the maximum and maximum. This is the maximum solution. You can treat this called as a nadir point or a maximum point, and this is called as reference point or ideal point. Okay, so for that you have to make a normalized roughness and normalized deflection. That is, you can roughness by maximum roughness, deflection by the maximum deflection. That is this value. This value is the maximum value. This is the maximum. Therefore, when you divide by those things, this value will be 1. This value will be 1. Other things will be within that. Okay. Therefore, this is your reference rectangle. Okay. Feasible solution. Feasible solutions. 1. This line is called as Pareto La points or Pareto solutions. Among the Pareto solutions are non-dominated solutions. Non-dominated means each one is good. That's all I can say. Each one is good. Each one is good. That is called non-dominated solution. There will be some more solutions there, and those are called as dominated solutions. That will not come because only optimizer will give only these non-dominated solutions, because your epsilon constant will bring you these only 4 solutions. That's all. So from that we find out something called as reference point. From that reference point, you find out what is the distance. What is how much distance it is for. If the distance, which distance is very close to your reference point, ideal solution or minimized solution, obviously that should be a good solution or a best solution. Therefore, this may be the reference point you can take. Another point I can say, for example, a reference point for sometimes a demand value. For me, my demand point may be here. I may choose this point as reference point, and I will find what is the distance for each point, and I may end up with 2. Okay, that is the minimum distance. That is for me. Therefore, this is more subjective in nature, but this point is more objective in nature. Okay, this ideal solution. From the, when you refer from ideal solution, this is objective in nature. You can treat your own demand value, and you can find out that is more subjective solution. So this is the knee point solution for each road. How the treatment cost varies is shown here, and you see that this is the mathematical provides an exact optimal solution. This is provide an exact optimal solution. But what happens? Consumes time and memory space. That is the problem. You have to have a little consume lot of time and memory space. Practically, it is not possible. Okay, practically it is not possible for more roads over a period of time. Okay, therefore you should have either a large computer. Okay, large computer. For example, for a large networks like government of Tamil Nadu, they can buy a large computers because it is a total department that can buy a large department. For an individual contractor or individual user, it is very difficult there. Okay, therefore that is a possible. That is a problem here. Therefore, in such cases, you have to go for another alternative that is called as meta heuristics. Okay, meta heuristics is another this. So before I go into this, I would like to ask the Dr. Rajan to respond. Dr. Rajan? Dr. Rajan? Dr. Rajan? Anyone from control room?
Sir, I will call Dr. Rajan sir and respond to you, sir. Is it fine, sir?
Okay, okay. Because it is again another process of going through it. Huh? So with this we will wind up because it is again another method of solving that.
Okay, sir.
Okay. Therefore, with this also we can wind up. We can keep another seminar on other things.
Okay, sir. Fine, sir. I think Rajan sir is connecting, sir, within few minutes.
Okay.
I just contacted him. Yes,
Ah,
sir.
Dr. Rajan.
hello. Yeah, tell me, sir.
Dr. We have concluded with mathematical modeling.
Oh, great,
And
sir.
we
Any
have
questions, sir? Please continue, sir.
Yeah. We have completed with the mathematical modeling.
Okay.
Okay, and we will have other models of those also there, but it is very
Okay.
difficult to in a single shell. Okay.
Yeah,
We
I
can
understand.
have it in a different. We can have it in a different time for other things.
Okay. No issues, sir. No issues.
Okay.
No issues.
Therefore,
Is there
with this,
any questions? Yeah. You can take the questions of the audience if any, and then you can close your session, sir.
yeah. I leave to the audience.
Yeah. Please. Audience, you can post your questions, or you can even unmute and ask. So whatever mode you want, you can do it. Shomana will coordinate.
Okay, sir. So, participant, as sir told, you can unmute your mic and even directly ask your question.
Actually, what happened now? See, after the great lunch, one who is talking continuously for 1 hour, for others it will be very difficult. I know pretty well. Thank you for your listening.
Thank you, sir. Thank you very much, sir.
Yeah, anybody who is interested to work on these areas can also talk to me over mail.
Yeah, please, any questions you can post, or if you want to send your questions through mail, you can please send to me. I will forward to sir, or I will give directly the mail ID of sir. Sir, if you don't mind, you can even post your mail ID in the chat box so that they can directly also.
Yes. Is it visible?
Yeah, sir. It's visible, sir.
Yeah. Please kindly note my email and phone numbers if you want. Okay. SAKTHIVELAN.ramchandran. Yes, is small. Okay. Any doubts also you can ask. Am I audible to everyone?
Yes, sir. You are audible, sir.
Yes, sir.
Okay, you can just if you have any doubts on that, and we can discuss. But the time is there for some more time. And before that, I have to thank the previous talk by Sir Shobna. Who is that, sir?
Dr. Arivalagan, sir.
Dr. Arvind, I should thank for what you call swapping the session. Actually, I should have come this morning itself. Since I have some other work, I have to get changed.
Thank you, sir.
Okay, Dr. Rajan. Yeah,
I think people think and get over this. Let them get back to you.
Okay, let them.
Mail ID.
Okay,
Thanks a
thank you
lot,
very much.
sir. Thanks a lot for giving a wonderful session today. Morning one session and afternoon session. Thanks a lot. Audience, please fill the feedback form. It is already being shared. And get back if you have any doubts or if you have any questions in this area, you can always contact Dr. SAKTHIVELAN, sir. Thanks a lot, sir. Bye for the day.
Thank you. Thank you, everyone.
Thank you, sir. So participant, so feedback link has been posted in the chat box. So kindly fill your feedback. And tomorrow, the final day, that is the 6th day of SCTP program, and the morning session will be given by Dr. A. Veera Raghavan, sir, at 10 a.m.